We've already looked at what our parent functions are, so I just want to kind of go back and revisit them and remind you of some things. We have our constant function. We can see the constant function is just a horizontal line. Our identity function, that's our linear function go through here. So this would be f of x equal to c. This is our f of x equal to x. Your absolute value function, f of x equal to absolute value of x. It creates a v at the origin. You've got your quadratic function, that's your f of x equal to x squared. Cubic, f of x equal to x cubed. Square root, f of x equal to square root of x. And definitely pause this video, rough sketch what these graphs look like, because we're going to be building on these graphs, as well as their equations. You've got your cube root. This is f of x equal to the cube root of x. The reciprocal function, which is f of x equal to 1 over x, and the reciprocal squared, which is f of x equal to 1 over x squared. What our goal in this section is, we want to take all of our parent functions and look at the different ways that we can transform them within an equation and on a graph. So this is leading us into what we really want to look at. Transformations of functions. There's many different transformations of functions that we can look at, so we're just going to kind of take it moment by moment here. The first one we want to look at is shifts. So we want to look at, just for example or reference, we are going to look at f of x equal to x squared as we look at this shift. A vertical shift is noted by when you take your original function and then add some value to it. If I add the value to it, that's going to create a shift upward. And so it would go up by c units. An example of this would be if I were to take, say, g of x being equal to x squared plus 3. Squared, it looks something like this. And look at what we can do with our g of x having the plus 3. What that's going to do is move every single point on the red line up 3. So I get something that looks like this. Now we can also look at this and say, okay, well, let's do another example and we use the same thing. What happens when I subtract? So if I were to take my f of x function and subtract c, that's going to move c units down. So this is your vertical shift down. And so I could take, again, another equation, say h of x equal to, I could take my x squared and say minus 5. Again, it's going to take your parent function that's red and move every single point down. 1, 2, 3, 4, 5. You still have a U shape. It's still facing upward. You have all those equivalencies. It's just been shifted up and downward. And again, this was just based off of attaching plus or minus a number. It's going to vertical shift it exactly like what you think. Now, this is one way that an equation can have additional numbers or subtraction in there, and it's going to shift your graph up and down. The next type of shift that we're going to look at is a horizontal shift. With the horizontal shift, let's look at a different parent function. We are going to look at f of x equal to absolute value of x. So let's just go ahead and graph that. So here is the absolute value of x graph. And so horizontal shifts, what do they look like algebraically? If we're going to do a left shift, it would be where we add in the addition of a number on the inside of the function. So again, an example of what that looks like, that would be when we have, say, the absolute value of x plus 3. So adding the 3 on the inside, you might assume from a number line that would move right, but with the horizontal shifts, it's the opposite of what you think. Because if I were to take this x plus 3 and set it equal to 0 and solve, I actually get negative 3. So this is a left shift. So with vertical shifts, it's exactly what you think, up and down. With horizontal shifts, it's the opposite of what you think. So graphically, it means I'm going to go to the left 3 units. I move everything on the red graph left 3. So 1, 2, 3. And so I get a graph that looks like this. Again, still maintaining its V shape. It's still an absolute value function. It's just been shifted left. The other type of horizontal shift is the right. And so with your right shift, this is when you actually have subtraction on the inside of the function. So this would be when I have h of x equal to the absolute value of x minus 4. Again, it's the opposite of what you think. So that would be 1, 2, 3, 4. And it would look something like this. And so those horizontal shifts are the opposite of what you think, and that's moving your left and right based on what is being added or subtracted on the inside of the function. So we have shifts that go up, we have shifts that go down. The next type of transformation we're going to look at is a reflection. With a reflection, we can have two types of reflections. We can have an x-axis reflection and a y-axis reflection. So for this one, I'm just kind of going through our different parent functions. We're going to look at f of x equal to the square root of x. So when we're drawing the square root of x, it looks something like this. So if we have an x-axis reflection, that is a negative multiplied on the outside of the function. So with our example here, that would mean we're looking at negative square root of x. It reflects it over the x-axis, so this gives you a curve like this. So similar, kind of just a swoop over, but it's just been flipped over the x-axis. And so let's look at what does the y-axis one look like. That is when it has the negative on the inside. So again, if I look at the negative on the inside of the square root, that would create a reflection over, that would create it over here. And so you can see it's being reflected over that x-axis. And you can see that this one is being reflected over the x-axis. Excuse me, I misspoke. But the main goal with this is that you can look at a certain equation and recognize what's being changed. And so we've got shifts that go up and down and left and right. And now we have this multiplier of a negative on the front, which is going to cause a reflection. The last type of transformations we need to look at are stretches and compressions. Now, you definitely want to use this section of your notes to complete the homework, but then on an exam situation, because we're not going to use our notes, we just want to understand what's going on. We don't have to have the exact vocabulary that's going with this one. So for this one, I'm going to go back to that absolute value function. So we're going to look at f of x equal to the absolute value of x. So let me just go ahead and put that on our graph for us. Okay, so this one, when you're looking at how is a stretch or compression happening, we can have a vertical stretch or a horizontal stretch or compression. With the vertical one, it is when we have a multiplier times our function out front. Now what's going to happen is when that a, and this is the part you're going to need in your notes for your homework, when a is greater than 1, this is known as a vertical stretch. So an example of this would be when you have g of x equal to 3 absolute value of x. What's going to happen is it is going to vertically stretch it. So the type of line that you get looks something like this. And so this would be 3 absolute value of x, whereas our original parent function, this was just without that multiplier. So this is known as a vertical stretch. The next thing you would encounter is when you have, again, that a multiplier, but this case, not that when it's bigger than 1, but when a is between 0 and 1. Now what we call that one is we call it a vertical shrink. Now you'll notice that we didn't go less than 1 because that would be negative, and that goes into the reflection. So we're not considering if there's a little negative there. We know that's reflection. So let's kind of look at an example, put some numbers to it. So if I had, say, g of x equal to 1/4 absolute value of x, it would look like this. That would be 1/4 absolute value of x. So what's happening is this is making it thinner, and this is making our function wider. But again, note-wise, here's what you're going to have to know. Vertical stretch is when you have that a greater than 0, and vertical shrink is happening when you have the a is between 0 and 1. Notes-wise, you really are going to have to use that for your homework. Exam-wise, I'm not going to make you know that very specific detail. Now let's look at what happens when we have a horizontal. Now in our reflections and in our shifts, when we had something on the outside of the function, that referred to our vertical. When we had something on the inside of the function, that was your horizontal. Same is true with your stretches and compressions. If I have f of, and let's put that a multiplier on the inside of the function, when a is greater than 1, it creates a shrink. And this is why you have to use your notes, because they switch up that wording. So a horizontal shrink occurs when a is greater than 1. Let's go ahead and write the next one down, and we'll do an example. When you have that multiplier on the inside, and again, it's between 0 and 1, this is known as a horizontal stretch when a is between 0 and 1. Example-wise, we'd say, okay, well then, let's look at, again, we're going to consider the same situation. That would be when g of x is equal to absolute value of 3x, or this would be the case of h of x equal to 1/4 x. And I'm not going to graph those two, but again, I just want you to understand the vocabulary and have this piece as you go forward with your notes. And so with all of these different transformations, we've got shifts, vertical and horizontal, we've got reflections, we can stretch and compression, and really at the end of this all, I just want you to be able to look at an equation and figure out what shifts and compressions have occurred. The last thing I want to pick up with this video is symmetry. So we're beginning to look at all these different parent functions, things that are being done to them. So the characteristic we want to pick up is, what about their symmetry? We can have two different types of symmetry. Right now we'll look at is an even function has symmetry over the y-axis. And what does symmetry over the y-axis mean? It means if I were to look at this y-axis, it would be the same on both sides of it. Now visually, I don't doubt that you could see the symmetry just looking at a graph. But what we want to do is we want to look at and do an algebraic test to look for that symmetry. So here's how you find that test. If you plug in a negative x into your equation and it gives you the original back or the same, then you have y-axis symmetry. So an example of that. Say we had f of x equal to x squared plus 2, and we wanted to know, does it have y-axis symmetry? Well, just like what you did with function notation, you plug in negative x into this situation. So if I plug in negative x here, I also have to plug it in here. Now, when I plug in negative x, I'm going to go ahead and do my algebra and clean that up. When I square negative x, that gives me x squared plus 2, which you can see is the same as the original. And so because it's the same or equal to our original f of x, this has y-axis symmetry. Notice if I graph that, that's a vertical shift of up 2. So I get this situation. You can see just looking at that y-axis that it's symmetrical on the same side. I could fold it at the y-axis and it would still give me the same function on both sides. Now, even functions have that y-axis symmetry. Odd functions have origin symmetry. Now we know that the origin is that point 0, 0 at the middle of our coordinate plane. With that origin symmetry, that means it's symmetrical over x and y-axis. And so what you're going to do to test for that, your algebraic test would be is if f of negative x is equal to negative f of x. Is a reflection on the inside and outside equivalent? Because again, those are our reflections, right? And so let's look at an example of that. We're going to work it with this function here. If I can take f of x equal to x cubed plus 3x, I can plug in negative x into this situation and it results in the other reflection. So let's see, that would be negative x cubed plus 3 times negative x. Cleaning that up, when I cube the negative x, it just gives me negative x cubed minus 3x. So we can see here that all the signs have changed. Note, I can pull a negative out. It gets me x cubed plus 3x. And that is negative f of x. So, picture-wise, this is an x cubed function. This looks something like this. And so you can see it has the reflective property or symmetry over this one and this axis. So if we were to flip it down and flip it over, we would get the same amount of symmetry. So just kind of the interesting thing that comes about of these even and odd functions, and we can talk about symmetry, but now we can add that into the conversation because we understand our shifts and transformations. So go and try the homework and contact your instructor if you need any assistance.